students, welcome back to Fluid Mechanics e-learning. This is a part of module 1 and we'll be learning about pressure and pressure laws and pressure applications. We all know fluid is a substance which can flow, and this fluid when at rest or in movement will exert some or the other pressure on the boundaries or objects that is going to intercept it. Now, we all know pressure is a basic entity, and this can be defined as the ratio of force by area. Now, what is force? Force is any magnitude or vector which can be applied in a particular direction, and this force per area is known as pressure. Now, if you can see this picture, we have pressure at a certain level. The pressure at the mean sea level is known as atmospheric pressure, and this can be given a value of 101.3 kilopascals. Now, what are the units of pressure? Now, pressure can be defined as force by area, and the unit for force is Newton, and area can be meter square. Hence, the units can be Newton per meter square, what is also known as pascals. If you have 1000 pascals, then it can be called as kilopascal, and if you have 1 million pascal, it is called as 1 megapascal or million pascals. So please remember, the conversion of pascal to Newton per meter square is equal on both sides. And we have pressure in terms of bar, which is given as 10 power 5 times the pascals, and we also have a CGS system of expressing pressure in pounds per square inch. Now let's understand how this pressure varies and what are the different types of pressure. Now if we draw a graph of the absolute pressure at 0 Kelvin and 0 pressure on the x-axis, then this level of the x-axis is known as absolute pressure, and the level above it is the atmospheric pressure, where the pressure of the air column that is going to act at the mean sea level is known as atmospheric pressure. Or we have our planet Earth has an atmosphere, and this atmosphere is made up of many gases, and these gases, which are also known as fluid, will be exerting some pressure on the people and objects on the Earth's crust. Now that is known as atmospheric pressure. Now any pressure more than atmospheric pressure is known as gauge pressure or gauge pressure. Any pressure lesser than the atmospheric pressure is known as vacuum pressure or negative pressure. Now by seeing this graph, we can understand that absolute pressure is the pressure which the reference from the absolute pressure 0 bar, and atmospheric pressure is a pressure at the atmosphere from the atmosphere on the mean sea level, and gauge pressure is higher than the atmospheric pressure, and vacuum pressure is below the atmospheric pressure. Hence, these are the 4 types of pressures. Now, as I was explaining what is atmospheric pressure or air pressure, if you can see, this is the length of the atmosphere, that is there, the width of the atmosphere. Then this much of the fluid that consisting of the atmosphere are going to exert some pressure on the earth, and that column is known as the air pressure for a given meter by meter area. That is, if you take this area as 1 meter by 1 meter, the air column that is going to exert pressure on this area will be known as atmospheric pressure, and the value is 103.2 kPa. Another way of understanding this atmospheric pressure and how it varies is, at the mean sea level, the average value of the atmospheric pressure is 101.32 kPa. But as you ascend upwards towards a hill or at Mount Everest, for an example, then the air column above you is going to be decreased, and hence the pressure at these peak points are lesser. Now as you go beneath, let's say you're going beneath the Earth's crust towards the magma or any trench, Mariana Trench or sea floor, then the air column above you will increase and the pressure over you will be higher. Hence, the peak points or the mountain points will be having low pressure, and the points beneath the Earth's crust will be having higher pressure. So, fluid pressure is the pressure exerted by any fluid, and usually it is equal in all directions. As you can see here, if you are swimming at a depth little higher, then the fluid that is going to act will be, the amount of fluid above you will be lesser. So this is a low pressure zone, and this is a high pressure zone. That means this much of water is already putting a pressure on your body. While in this case, the pressure of the fluid is going to be less because the amount of fluid over you is going to be lesser compared to the other picture. Hence, pressure increases with depth. So how do you measure water pressure? Again, as you know, pressure can be measured using a pressure measuring gauge or pressure gauge. And the best example is checking the pressure from your shower. When the flow from the shower is nil, the pressure is quite low. When you have a high flow from the shower, you can see the pressure going to be higher. And as you know, if the pressure from your shower nozzles are high and with high velocity, then you have the fast moving jet that is going to come out from the shower. Same way you can observe this picture here, an example as to understand what is low pressure, what is high pressure. If you can take a beaker full of water and make 3 holes, the water that is going to come out from the top hole will be very less. I mean, the force with which the water that is going to come out from the first hole will be quite low because the column of liquid that is going to contribute to this flow will be quite low. But let's come to the second hole or opening that is there. The column of liquid will be half of the beaker, but at the bottom the flow will be very high, and you can see the flow going little further because the column of liquid having high exerting pressure on this hole will be quite high. So as from this you can observe that if the depth of the column of the fluid is high, then the pressure is also going to be high. So the deeper you go, the pressure is higher. If you ascend upwards, then the pressure is going to be lower. So coming to this, with this kind of a basic, then we will understand what is Pascal's law. Pascal's law states that the fluid pressure exerts the same intensity of pressure in all directions. For example, if you have a sponge filled with water or soaked with water, and when you press, the water will squeeze out in all directions. It will not only squeeze out in x direction or y direction or z direction. That means water will erupt or exert out in all directions. In other words, Pascal's law states that the intensity of pressure of the fluid at rest is equal in all directions, that is x direction, y direction and z direction. So mathematically we can say that the pressure in x direction will be equal to pressure in y direction will also be equal to the pressure in z direction. That is px will be equal to py will be equal to pz. Since we have 3 directions here, we will be considering a triangular element having the sides A, B, C, and the side AC is dx, AB is dy, and the length of the side BC is ds. Now since we know pressure is the normal force by area that is going to be acting, so we have to consider normal forces, that is on the x-axis, along the x-axis, the pressure that is going to be applied will be Py, not Px. And in the y-axis we have the pressure that is going to be applied is Px, and here we have a normal pressure that is going to be applied as Pz. Hence force will be equal to intensity of pressure into the area. Now intensity of pressure is Py, and the area of this element across AC will be equal to dx into 1, where 1 is the thickness of the element. The same picture is shown there. We have to resolve the inclined forces. So coming to this picture here, you can see we have Py acting at dx, Px acting at dy, and Pz acting at an inclined force at an angle theta, whichever as we have defined for the angle ABC. Now when you resolve this inclined force, we'll have Pz cos theta and Pz sin theta, and hence when we do the resolution of forces across x-axis, the forces that are going to occur is the pressure force across all the normal surfaces and weight of the element in the vertical direction, which we will be actually neglecting in this case. So let's take resolving the forces in x direction. We have which are the forces that we will have in x direction. That is, we have Px into the area of AB, that will be Px into dy into 1 minus Pz or Ps into the area of BC here. So BC into 1, but it is the vertical x direction that we are going to consider. Hence the resolution will be Ps sin theta or PS 90 degree minus theta, it is nothing but cos theta, and when you simplify, we'll end up with Px is equal to Pz. Same way, let's resolve in y direction. In this case, we have Py in the y direction upward, which is positive, and Py into the area of AC, that is Py into dx into 1, and the vertical component of Pz. But vertical component of Pz is Pz cos 90 degrees minus theta into the area of BC. Area of BC is the thickness, that is 1 into ds. When you do that, and when you consider, you can neglect the weight component, you'll end up with Py is equal to Pz. Seeing the equations Px is equal to Pz and Py is equal to Pz, we will end up with the equation Px will be equal to Py will be equal to Pz. Now this will prove the Pascal's law. Now what are the different applications of Pascal's law? Now as I told you, Pascal's law states that if a pressure is applied on any object, the pressure from the fluid will be same in all directions. Now if you can see any hydraulic brake or hydraulic jack or hydraulic lift, this works on Pascal's law. Let's assume there's a plunger here on the left hand side and a ram on the right hand side. Now it's beautiful concept that when you apply a force on this small cross section of area of a plunger, now this is filled with the plunger and the ram are filled with a fluid, maybe oil or any gas, and these two act like piston, and when this force is pushing the oil or the fluid filled here, then what will happen, automatically the fluid pressure in this direction will increase. Now please note, this can happen only if the pressure intensity in all three directions are same. If it were not, say if pressure intensity of a fluid pressure is increasing only in x direction, then this won't be lifted, or if it is only in y direction, this won't be lifted. It is only because the pressure intensity in all the three directions are equal that the amount of force that you're applying is uniformly distributed on the fluid, and the fluid pressure is going to be common across all the three axes, and then it is going to lift your weight that is going to come on the ram. Now why is this a beautiful concept? Because with small application of force on the plunger, you can lift heavy loads and heavy cars on the ram. The magnification of force lifting or weight lifting will be seen when you solve a few problems. If you can see, the area of cross section of this plunger is about say 1 meter square, while the area of cross section of the ram maybe is about 30 meters square, and the force you're applying here is about 100 Newton, then the force that you're going to lift will be equal to the ratio of P by AP into your area of cross section of the ram, AR. That is the ratio of force applied on the plunger to the area of the plunger should be equal to the force that is lifted on the ram divided by the area of the ram. That is how a hydraulic lift or hydraulic jack works. Now you would have seen all this in your malls where multiple story parkings, car parking is going to be there. Even in our own campus where we have hydraulic lifts where you use every day to climb many stories of the building. And what is a hydraulic brake? This picture shows you very clearly how a hydraulic brake will work. As a driver applies the brake and puts some force on the brake pedal, this brake pedal is connected to a small cylinder, and this small cylinder will have some oil which will be exerting some pressure on the brake disc here. Now when this force is applied, the fluid inside the cylinder will expand, and this expansion will make sure the brake, the tire is expanded and the brake is going to be applied. Now that is the first law of pressure that we discussed. Now we have the second law of pressure, which is known as hydrostatic pressure, and it states that the rate of increase of pressure in the vertically downward direction is equal to the specific weight of the fluid. That is, if we have an object immersed in a fluid at rest, and the pressure at the force at the face AB and the pressure at the bottom face will have a difference. The pressure at the bottom will be higher than the pressure at the top, or the deeper you go, the pressure will increase. Now to prove that mathematically, we have the mathematical equation P is equal to density into acceleration due to gravity into the depth at which you're talking about. So the hydrostatic law states that the rate of pressure variation with respect to the depth, here dP is the variation with respect to dz. Dz is the depth that we are going to talk about, is equal to the specific weight. Specific weight is nothing but your density into the acceleration due to gravity, which we have discussed in the previous classes. Now to prove this, we have a figure that can be shown here. Let's understand the derivation. We have a object that is immersed in a fluid at rest, and there's a pressure acting on the first face AB and also at the bottom of the object, and this object is at a distance Z from the free surface of the fluid. And because there's a pressure P at level AB, and as we go below, we have assumed that the pressure is going to increase. And at what rate is it going to increase? It is increasing at dP by dz. It is increasing at a rate of dP for a length of dz. This length is dz, and into the total length delta z. This is a total length of delta z. So what are the forces acting on this object? We have the pressure force on AB, which is nothing but the pressure force P into the area of the object, and then we have the pressure force on CD. This is the second part, which is CD, and that is given as the increased pressure, that is P plus rate of pressure increase, that is P plus dP by dz into delta z into the area of the cross section of the object. Hence, when you also have the weight of the self weight of the object W, it is given as density into acceleration due to gravity into volume. Density, let's assume it is rho, into G into volume is nothing but area into the thickness, that is delta A into delta Z. And when you equate all these forces, we'll end up with, that is the first pressure on the first face AB, then we have the pressure upwards at the bottom P plus delta Z into the dP by delta Z into dz into delta Z into delta A, plus the self weight rho G into delta A into delta Z, that is the total weight it is going to act. And further, when you simplify, we'll end up with delta P, dou P by dou Z will be equal to rho G. And when you integrate it on both sides, we end up with P is equal to rho G Z. Z is nothing but your vertical movement, that is depth of depth from the free surface, that is Z. In some textbooks, they've given it as H. So we can express the equation as P is equal to rho G Z or rho G H. Okay, continuing with the derivation, as to understand how this derivation works and what it expresses. We have the sea level, and as we go below, let's say we are talking about some trench at the sea floor, then you can see the pressure is going to increase, because at 10 meter we have 10 meters of water that is going to exert pressure at this level. And when we know that P is equal to rho G H, so H will be 10 meter here, so P will be equal to 1000, that is rho for water, into 9.81 into 10. Let me go to 20 meter, then the pressure will be rho G H, but H is 20 meter here, so the pressure is going to increase. So if I keep going below, the pressure at the bottom of the sea will be very much high as compared to the free surface. So this is what we were trying to express. At 0 meter, we have about 1000 hectopascals or atmospheric pressure, and above this will be the lesser pressure. You can see 600 hectopascals, 700 hectopascals and 900 hectopascals. But as you go deeper into the earth, the pressure is going to increase. The same thing can be mapped to the elevation and the decrease. So hectopascal is a unit of pressure that is equal to a millibar. Now that we have learned about pressure, now we have to understand how do we measure this low pressure or high pressure or atmospheric pressure and give a value for this. So we have many devices to understand and measure this pressure, and that too especially fluid pressure. So the major devices that we have are barometer, which directly measures the pressure for you, and then we have manometers, which are the traditional devices to measure pressure, and the latest ones are based on the mechanical working, that is known as mechanical pressure gauges. So we have three basic classification: the barometer, the manometer, and the mechanical gauges. Lately we are dealing more with the digital pressure gauge, where if you just insert the device wherever you want to measure the pressure, it will give the pressure to you directly in your digital format. Now, in manometers, you'll have to learn about various types of manometers. That is, we have simple manometer and differential manometers. And simple manometers can be further classified as piezometer and the U-tube simple manometer. And differential manometer is classified further as U-tube differential manometer or inverted U-tube differential manometer. And mechanical gauges are further classified as diaphragm based working pressure gauge or Borden's pressure gauge, which is a small tube connected to the needle, and if the tube expands the pressure will increase and the tube contracts the pressure will be decreasing. And the dead weight pressure gauge, which works on an oil and a ball setup, and bellows pressure gauge. Now, how do we should also know which device measures what type of pressure. So we have the gauges or pressure gauges. They measure the atmospheric pressure majorly, and these can be used in your car tires, and you can use for hydraulic applications. And then we have the sealed pressure gauges, which refer to the atmospheric pressure and gauge pressure measurement, and this can be used in industrial application, and where you need intensive cleaning with water, like your tank cleaning and pressurized cleaning, then you'll be going for a sealed pressure gauge. And then we have to measure the absolute pressure or the vacuum pressure, you have a barometer similar to that, and we have differential manometers which can provide you the readings between two different points. So we have, if you want to measure the pressure in an air conditioner, cleaning, cooling, that especially for gases, then you'll go for a differential pressure device. So coming to manometers, what is a manometer? Manometer is a pressure measuring device which measures the fluid pressure at a given point. And in this we have two types. One is simple manometer and the other one is differential manometer. So in this slide you can understand what is a simple manometer. Simple manometer is a small tube which is connected to the point where you want to measure the pressure, and the other end of the tube is open to atmosphere, just like this. Imagine this is a cross section of the pipe and I want to measure the pressure at point A. Then I will connect a small tube in the shape of a L, okay, and then this tube is connected to the pipe and the other end of the tube is open to atmosphere. The same thing can be connected to a tank as well, and this small tube is the simplest form of the manometer, which is known as your piezometer. Now how do we measure pressure here? We will measure the height of resin fluid, and we know that by hydrostatic law P is equal to rho g h, and this is this height. By measuring this height I can find out the pressure by the equation P is equal to rho g h. Now a question for you to think about is, when will the fluid raise in this piezometer? The fluid will raise only when the pressure inside the pipe is higher than the atmospheric pressure. Only when you have high pressure in the pipe, the raise will be there. Higher the pressure in the pipe, higher the height or rise of the fluid in the tube. Same way in the tank. Now in the tank, you can observe that the water level in the tank and the water level in the manometer are same. That is because the tank is also open to atmosphere and the tube is also open to atmosphere. In case if the tank was closed, then there will be a higher rise in the piezometer than your level of the water, because area of the tube is very less. So this is the piezometer, is the simplest form of manometer, with one end connected to the point where you want to measure the pressure and the other end open to atmosphere. The pressure is measured as the raise of fluid H, and P is calculated as P is equal to rho g H. Rho is the density, G is 9.81 meter per second square, H is what you will be measuring from the piezometer. Now coming to the second type of U-tube manometer, second type of simple manometer is a U-tube manometer. This is similar to piezometer, but just to overcome the length of the piezometer that is going to be provided for higher pressure measurement, they have the manometers have evolved to use a denser fluid instead of a lighter fluid to measure the pressure. A YouTube simple manometer is also a manometer connected to a point where the pressure is to be measured. For example, this is the pipe, but it has a U shape fitted with the manometric fluid. Now you can see this red fluid is a denser fluid as compared to the fluid flowing in the pipe, so that you don't have to have a longer tube to measure the pressure. Now you also have to understand YouTube simple manometer can measure gauge pressure and also it can measure vacuum pressure. Now how do we read a YouTube manometer? This manometer, YouTube manometer, this is known as the left limb and this is known as the right limb. This left limb, the pressure on the left limb is always balanced by the pressure on the right limb. So if I take a level or a datum at point 3, then I have the pressure of the fluid in the pipe as PA, and the height of fluid that is going to be there from the datum in the left limb, that is given as rho g h of this, is balanced by the pressure of the raise of the fluid on the right limb. So we'll have rho g h, so density of this fluid versus the density of the manometric fluid. What is a manometric fluid? Manometric fluid is a denser fluid that is going to be consisting in a manometer, and this manometric fluid should be immiscible with the fluid that is going to be measuring in the pipe, and it is usually denser because we can reduce the height of the tube that we can be giving, and we can measure higher pressure for the shorter tubes. So in this second type of manometers are known as differential manometers. Sorry, this is for a simple manometer, but in the case of gauge pressure, as I told you how to measure the manometer here, we have the pressure of fluid in the pipe, and then we have the fluid level at a datum xx, and we have this has h1 and this has h2. Then we have the equation P will be equal to G into rho 2 h2 minus rho 1 h1. Same way we can balance out for vacuum pressure in case of a vacuum measurement. So this is the inverted manometer. In the similar to the other manometers, we have a inverted U tube connected here, and this is suitable for lighter measurement and lighter fluids. So what are the pictures of manometers? This is a typical YouTube manometer. You can see the mercury that is there, and these are the gradations to measure the rise of fluid, and this is a blood pressure measurement device, and this is a mercury based device where you can see the blood pressure being measured from our own body, as a rise in fluid is the mercury. So another picture of other measuring devices, that is we have the Borden's YouTube gauge. This is a mechanical pressure gauge consisting of a small tube which is known as a Borden's tube, made of alloy of copper and a copper alloy, and this tube is very susceptible to small pressures. This tube can contract and it can expand depending on the pressure application, and this is connected to a pressure intel and the gears mechanism with the needle. When a pressure is applied to the socket here, then the tube will expand and the needle will move, and when the pressure is released or taken or withdrawn, then it will come back to its own position and the needle will drop down. This is how Borden's pressure gauge works. So what are the different types of mechanical gauges that we have? We have bellows pressure gauge, we have diaphragm, and a Borden's tube. Bellows is like a spring, it acts under pressure, contracts under pressure and expands under pressure. The mechanism is connected to a needle, so depending on the force that is going to be applied, it can move to that extent. Same with diaphragm. Diaphragm is like a elastic support that is going to provide it, and this also deforms under some certain pressure, and the deformation can be seen in a needle movement. So this is how actual pressure gauge will look. Behind this, all the mechanisms like this Borden gauge will be there, and over this we have a face cover or a cover sheet with all the gradations that is going to be there. Now all of you would be familiar with this type of a mechanism. Whenever you go and fill air for your vehicles or the tires, we have a device called digital tire inflator, and this is usually given in the unit of pressure, that is pounds per square inch. And we have a air compressor. This will be a air compressor which is attached to the pipe inside the device, and this air under compression is passed, and we have a gauge to calibrate it, and this will give us how much actually the pressure is. When you set it to 36 or 26, only that much of pounds per square inch of pressure is going to be released into your tires, and this is digitally represented, but you have a gauge which will also measure the same for calibration. This is known as a tire pressure inflator. So we have learned about pressure, types of pressure, Pascal's law and hydrostatic law, and pressure measurement using manometer and gauges. Thank you.